Greetings of the day to all of you. We resume our lectures on advanced power electronics. In the previous lectures, we have started with non-isolated DC to DC converters and predominantly discussed buck converter in detail with the design of passive elements, the role of switching frequency. We have done waveforms for CCM and DCM and the boundary condition between CCM and DCM and how to design the converter parameters to ensure that your converter operates in continuous conduction mode, the effects of DCM, and a little bit discussion on non-ideal buck converter. I shared some questions with you which I hope you must have solved by now, and in today's lecture we move on to DC to DC boost converter circuit. So as the name suggests, DC to DC boost converter is essentially a converter that gives you output voltages that are greater than or equal to the input DC voltages. So it is a step up chopper that gives you voltages of higher magnitude with respect to the input. It's one of its most important applications is in solar energy conversion systems, where you generally want to boost the voltage of solar arrays, solar panels, before making it reach a value where it can be effectively converted into AC. So stepping it up or performing maximum power point tracking of solar power arrays. You also used boost converters in electric vehicles, many other renewable applications, and sometimes in regenerative control of DC motor drives. So what does a boost converter? And it is essentially very important because a buck operation was still convenient with DC supplies before power electronics, but a boosting operation with DC supplies has been made very, very convenient through the boost converter. Stepping up DC was very inconvenient before power electronics, but with boost converter, with power electronics and switching devices, with the design of boost converter, step up of DC has become very easy. So let's see how the circuit looks like. You have an input voltage VDC, and you have an inductance often known as a boost inductance in series with the source. You have a fully controlled device connected across this combination, and then you have a fast recovery diode in series, a capacitance across the load, and this is how your circuit gets completed. So you have a switch, you have some inductance, some capacitance, the load resistance, and this is the load voltage V0 that is developed across the load, and you also have a freewheeling diode. You know that this device S, the switch used over here, is a fully controlled device as used in all DC to DC converters, and it is switched at a very high switching frequency. Assuming that you're giving some switching pulses to this device, you are going to analyze the circuit behavior. So when the switch is on, which is often referred to as the energy storage interval, let's see what happens during that interval. Now when the switch is on and you are supposed to store energy in the inductor of the circuit, so the switch is on, it's conducting, the source is delivering energy and storing it into the inductor over here. The freewheeling diode over here is reverse biased because I'm starting the analysis of the circuit with the assumption that it is operating as a boost converter, and in steady state this voltage is generally higher than the input voltage, so the cathode is at a higher potential than the anode, as a result of which the diode is reverse biased. Even if you don't assume it, like when the converter is about to start, there is no potential over here, so obviously this is a short circuit path, current will take this path and this becomes reverse biased, so this diode is not conducting. And then you have the capacitor, which is still delivering into the load, assuming that it has some previous state of potential. अगर हम steady state की बात करें तो it will have some previous state of energy, and it will deliver energy into the load when it is, when the load side is disconnected from the source in the energy storage interval. You call it the energy storage interval because the inductor is storing energy right now. The capacitor is in fact losing its energy, unlike a buck converter where it could be storing or losing energy. But here in a boost converter, the capacitor is losing its energy, and the load is continuously receiving energy from the capacitor. So this is from 0 to dTs. During this interval, the voltage, let's see the voltage across the inductor. Over here, let's define it like this, VL, and if this is VDC, so VL is simply equal to VDC. Also, voltage across the switch is 0 because it is conducting. Let's call it SW. Okay, then voltage across the freewheeling diode, because this is how the freewheeling diode is connected with the positive anode this way and the cathode this side. So let's define it like this. The voltage across the freewheeling diode is how much? Minus of V0 if you simply apply KVL. The voltage across the freewheeling diode is minus of V0. Minus is important because we know that when the device is not conducting, at that point in time, it has to only block voltages that are negative in whose magnitude is that are negative voltages. Diodes can only block negative voltages. So when it's not conducting, some negative voltage must be coming across it. So this is negative voltage coming across the diode, which essentially makes it reverse biased, and that's why it does not conduct. What else? The load voltage or the capacitor voltage is actually falling in magnitude because the capacitor is losing its energy, and the inductor current is rising because the inductor is storing energy, also because the inductor voltage is positive, that is VDC. So I think that's all about the interval 0 to dTs. Now from dTs to TS, the switching pulse is withdrawn. So when the switch is off, it is the energy releasing interval in the context of the inductor. So let's see what happens then. So your inductor was previously storing energy through the switch. The switch has been turned off. It looks like the inductor circuit has been suddenly disrupted or interrupted, as a result of which the inductor voltage will switch in polarity like this, and it will ensure that this magnitude of this voltage is enough to deliver energy through the freewheeling diode. It will forward bias the freewheeling diode and dump this energy into the capacitor and into the resistor. Okay, so now due to this high magnitude LdI by dt kick, because you had interrupted current in a very small interval almost instantaneously and made that current apparently zero, a very high magnitude negative voltage spike is induced here because of a classic inductor behavior, which forward biases your freewheeling diode, and hence this inductor starts delivering energy, this energy that it had previously stored. It now starts delivering it into the load and into the capacitor. Now right now you can see that the capacitor is connected with the inductor. It could be taking energy from the inductor, and the load will always take energy, so the load could also be taking energy from the inductor as well as from the source, because source is also connected here. Or it could be that the inductor is delivering energy into the load, and so is the capacitor delivering energy into the load, because maybe the load demand is high. So you don't really know whether the capacitor is taking energy or the capacitor is giving energy, but you have to ensure that in this interval, in this particular interval, which is say dTs to TS, in this interval your capacitor should be essentially storing energy मोस्टली स्टोरिंग एनर्जी, क्योंकि इससे पहले वाला जो इंटरवल था उसमें कैपेसिटर डेफिनेटली एनर्जी को सिर्फ लूज़ ही कर रहा था. अगर यहाँ भी कैपेसिटर एनर्जी लूज़ करता रहेगा देन इट्स व्हेन विल इट गेन दैट एनर्जी. सो द कैपेसिटर हैज़ टू बी डिजाइंड sufficiently big enough that it stores energy in this interval, then delivers energy in some another interval. So it's ideally desired कि इस interval में आपका कैपेसिटर जो है वो एनर्जी को स्टोर करे. Okay, so now let's see the waveforms during this interval. So the waveforms are like this. Your inductor voltage, let's stick to the polarity that we had chosen. This is the polarity VL. The inductor voltage right now is, if this is VDC, then this is V naught, then VL is equal to VDC minus V naught. Now look at this. पहले इंडक्टर वोल्टेज VDC थी, अब इंडक्टर वोल्टेज VDC माइनस V naught है. This itself tells you that if it was previously positive, that means the inductor was storing energy. Now VL should be negative so that the inductor is actually releasing energy. At every point in time we have to ensure that volt second balance is maintained. For that to happen, that is for VL to be negative, it is essential that V naught should be greater than VDC. सो बेसिकली ये जो इंडक्टर है इसका जो नेचुरल टेंडेंसी है बाय डिफॉल्ट टू मेंटेन इट्स वोल्ट सेकंड बैलेंस, दैट इनडायरेक्टली इंश्योर्स दैट वी नॉट इन दिस सर्किट इन सच अ कॉन्फ़िगरेशन, जब डिवाइसेस ऐसे कनेक्टेड हो बूस्ट कन्वर्टर में, तो जो वोल्ट सेकंड बैलेंस है उससे खुद ब खुद इंश्योर होता है दैट योर वी नॉट इज ग्रेटर दैन वी डी सी. दैट मीन्स योर कन्वर्टर शुड ऑलवेज ऑपरेट in the boost mode, that the output voltages should be greater than the input voltages. So this is the first thing, VL is equal to VDC minus V naught. What about the voltage across the switch? The voltage, let me write it here, VDC minus V naught in the other interval. Voltage across the switch, it is not conducting. So what is the voltage across the switch right now? The switch is connected like this. It is directly connected across the load because the freewheeling diode is conducting. So the voltage across the switch is V naught and plus V naught, positive voltage. So this device that you have to choose, this device has to carry only positive currents and only positive voltages have to be blocked by this device. It has to block only positive voltages. Therefore, you can use a single quadrant fully controlled switch. So then you can choose an IGBT or a MOSFET over here. तो ये हो गया voltage across the switch. What about voltage across the freewheeling diode? It is conducting, so that voltage is 0. What about V naught? V naught is a capacitor voltage or the load voltage. Ideally it should be rising, but it might be falling depending upon whether the capacitor is losing energy or it is gaining energy. But like I said, that ideally it should be gaining energy, so it should be rising, the voltage across the capacitor. What about the inductor current? It should be falling because the inductor is losing energy into the capacitor and into the load. So this capacitor over here in a boost converter circuit, if you observe, it has a couple of roles to play. The first role that it plays is that it ensures that the load is never deprived of energy. Energy storage interval हो, यानी कि 0 to DTS हो या DTS to TS हो, capacitor अगर load के across connected है तो load will always continuously receive some energy which will smoothen out the waveform of load voltage. That is one role. That is, it ensures continuous supply of energy to the load. It ensures a filtered load voltage. That is the first role. The second role is कि जब आपका एनर्जी रिलीजिंग इंटरवल होगा तो आपकी इंडक्टर ने जितनी भी प्रीवियसली एनर्जी स्टोर की होगी, जब वो उस एनर्जी को लोड में देगा, लोड को उतनी ही एनर्जी लेनी है दैट द लोड इज डिजाइंड टू टेक. वेयर डज द रेस्ट ऑफ द एनर्जी गो? It gets dumped into the capacitor. So the capacitor takes all the energy that was, the energy mismatch between the inductor and the load resistance. In दोनों के बीच में जितना भी energy mismatch होना है, that is going to get absorbed in the capacitor itself. So that's how the it protects the devices by taking in that extra energy. So this was about the role of the capacitor. What else? I think this is it. Now let's quickly draw the waveforms. we have this information with us. So if we draw the waveforms, we have 0 to DTS, the pulses say VGS if you use a MOSFET. 0 to DTS, the pulse is high, and then DTS to TS, the pulse is low. So the switch is conducting and the switch is not conducting. During this interval, the inductor is storing energy. So the inductor current is rising, and then the inductor is definitely releasing energy. So the inductor current is falling, rising, falling, and so on. Moving on, if you draw the inductor voltage, it is initially in this interval, it is positive and it is VDC. In the next interval, it is VDC minus V0, which is negative. It has to be negative because VDC is less than V0. We have boosting operation, and then positive again VDC, something like this. So by volt second balance, we will ensure that area under this is equal to area under this. We'll apply that mathematically and check it out. What else? We can draw the load voltage. Now the load voltage is falling in the first interval, and ideally it should be rising in the other interval and then falling and so on, right? And the capacitor, this is the capacitor voltage or the load voltage. And then we have the, what else? The voltage across the freewheeling diode. The freewheeling diode in the first interval is not conducting, and its voltage was minus of V0. And then it was conducting, so this voltage was 0. And if we draw voltage across the switch, initially it was conducting, so 0. And when it was not conducting, this voltage was plus V0. So interestingly, one more thing to observe is that if you are using a boost converter whose input is 100 volts, the devices are subjected to a magnitude of V0. यानी कि आपकी जो आउटपुट वोल्टेज, जो मैक्सिमम आउटपुट वोल्टेज होगी बूस्ट कन्वर्टर की, उस रेटिंग के डिवाइसेस आपको चूज करने हैं, बोथ फ्री व्हीलिंग डायोड एज वेल एज योर MOSFET or your main switch. Unlike a buck converter where the rating is decided by the input, the boost converter circuit has to be constructed in such a way that you choose devices, the ratings of the devices are chosen as per the output voltages. ये आप देख रहे हो कि जो भी आपके devices हैं वो output voltage के magnitude पे stress हो रहे हैं, तो it has higher rating of devices, the boost converter. One more thing about boost converter, interesting thing is कि अगर आप इसकी source current देखो, this is the source current. It also happens to be your inductor current. ये है आपका source current या inductor current का waveform, because it's the same current is connected in series with the source, right? यानी कि जो आपका boost converter है उसका source current या inductor current same चीज़ है, और जो ये current है you have already drawn its waveform. It is if your converter is operating in CCM, this particular current is continuous. एक डीसी सप्लाई से एक कंटिन्यूस करंट निकलना, यानी कि प्योर डीसी करंट, जितनी कंटिन्यूस होगी उतना प्योर डीसी होगा, दैट इज गुड, दैट इज विच इट इंश्योर्स दैट ए गुड हेल्थ ऑफ द सप्लाई. बक कन्वर्टर में जो आपकी सोर्स करंट होती है, क्योंकि उसमें बीच में ही स्विच कनेक्ट होता है, स्विच ऑफ हो जाएगा तो आपका सीरीज में ही सोर्स के साथ कनेक्ट होता है, तो जैसे ही स्विच ऑफ हो जाएगा आपकी सोर्स करंट इंटरप्ट होती है बक कन्वर्टर में. तो बक कन्वर्टर में क्या होता है, यू हैव अ हाईली पल्स्ड ऑन ऑफ होती है आपकी सोर्स करंट, जिसकी वजह से आपका सोर्स जो है इट कैन ऑल्सो गेट अ डीसी सोर्स कैन गेट डैमेज्ड ओवर टाइम. बट इन अ बूस्ट कन्वर्टर द सोर्स करंट इज कंटिन्यूअस ड्यू टू द प्रेजेंस ऑफ एन इंडक्टर इन द सोर्स, which ensures that supply is connected to a boost converter further. These supplies, their health is better maintained as compared to buck converter. This was another thing. अब अगर आप एक और चीज़ देखो, कैपेसिटर करंट की बारे में आई वांट टू टॉक टू यू अबाउट द कैपेसिटर करंट. जब आपका स्विच ऑन था, लेट्स सी दैट सर्किट अगेन. Let's see that part again. When your switch was on, the inductor was storing energy like this. The diode was not conducting. And if I have defined IC like this and I not like this time IC is equal to minus of I naught. ये माइनस साइन ये भी इंडिकेट कर रहा है that the capacitor is actually discharging, right? I can reverse my conventions completely, okay, but it's generally better to use a convention that denotes minus as discharging. You can very well use plus as discharging, that doesn't change anything. But ये IC जो है इस टाइम पे माइनस ऑफ आई नॉट के बराबर है, ठीक. और जो दूसरा इंटरवल है, जब आपका डायोड कंडक्ट करता है और स्विच ऑफ हो जाता है, तो जो आपका IC है, इट इज दैट टाइम IC is equal to IL minus I naught. Simple IL यहाँ से आ रहा है, I naught, if this is IC, this is IL and this is I naught, apply KCL, you will get IC is equal to IL minus I naught. Now I'll write this information somewhere separately. कि पहले इंटरवल में IC इज इक्वल टू आई नॉट और दूसरे इंटरवल में IC इज इक्वल टू IL माइनस आई नॉट. अब आप यहाँ आ जाओ फिर से. ये V नॉट जो है ये इट लुक समथिंग लाइक दिस, ये हमने देख लिया. जो आई नॉट होगा वो आप अज्यूम कर लो इट विल हैव मोर और लेस सेम वेव फॉर्म इफ़ यू अज्यूम अ रिपल फ्री अप्रॉक्सीमेशन जो हम जनरली स्टेडी स्टेट एनालिसिस में करते हैं. आई अज्यूम इट्स अ वेरी बिग कैपेसिटर, द लोड वोल्टेज इज ऑलमोस्ट फ्लैट एंड हेंस द लोड करंट इज ऑल्सो, लेट मी ड्रॉ इट इन ब्लू, द लोड करंट इज ऑल्सो ऑलमोस्ट फ्लैट आई नॉट, ठीक है. ये भी ऑलमोस्ट कंप्लीटली फ्लैट है. तो जो आई सी है, इफ आई वांट टू ड्रॉ द वेव फॉर्म ऑफ आई सी, let's create some space here. If I want to draw the waveform of IC, पहले तो वो माइनस आई नॉट है, so something like this, माइनस आई नॉट. और जो दूसरा इंटरवल है उसमें it is IL minus I naught and it should be charging during the whole interval. यानी कि IL जो होगी वो I नॉट से बड़ी होनी चाहिए, तब ही आपका IL माइनस आई नॉट पॉजिटिव आएगा. IL शुड बी ग्रेटर देन I नॉट. अब ये चीज देखो, IL जो है इट इज अ सोर्स करंट, सो IL को मैं कह सकती हूँ इट इज IDC या IS, वट एवर आई वॉन्ट टू कॉल इट. अगर मैं सोर्स साइड का वोल्टेज ले लूँ VDC और उस VDC सोर्स में से करंट निकल रही है IL बिकॉज IL इज कनेक्टेड डायरेक्टली थ्रू इन सीरीज विद द सोर्स, ये मेरा इनपुट का पावर देगी मुझे, ठीक. और जो मेरा आउटपुट का पावर है वो है V नॉट इंटू आई नॉट, ठीक. ये दोनों बराबर होने चाहिए. इफ आई एम निग्लेक्टिंग द स्विचिंग पावर लॉसेज, बेसिकली आई एम एसेंशियली एक्सरसाइजिंग द इनपुट आउटपुट पावर बैलेंस. जो इनपुट का पावर इनपुट से निकल रहा है वो आउटपुट में डिलीवर हो रहा है. दिस इज पावर बैलेंस, राइट. नाउ इफ इट इज अ बूस्ट कन्वर्टर देन V नॉट, दिस पर्टिकुलर थिंग इज ग्रेटर देन VDC, यानी कि ये वाली टर्म बड़ी हो गई, राइट. सो दिस टर्म इज ग्रेटर देन VDC. Automatically IL will be greater than I naught. सिंपल, जैसे ट्रांसफॉर्मर में भी होता है ना कि प्राइमरी अगर सेकेंडरी पे स्टेप अप हो रहा है तो प्राइमरी की करंट बढ़ती है. सिंपल, इट्स लाइक, इमेजिन इट लाइक इन टर्म्स ऑफ पावर, इट्स लाइक अ ट्रांसफॉर्मर. तो दिस इज योर प्राइमरी साइड करंट, इट विल ऑब्वियसली इंक्रीज. यानी कि IL जो है वो I नॉट से बड़ा होगा. अगर V नॉट VDC के ट्वाइस है तो IL I नॉट के ट्वाइस होगा, which means that if it is boosting, if it is V naught is greater than VDC, then definitely IL is greater than I naught. And when IL is greater than I naught, then definitely IC in this interval is positive. That means definitely in this interval the capacitor is storing energy. ठीक है. तो अगर आपका वोल्ट सेकंड बैलेंस इंश्योर करता है, वो वोल्ट सेकंड बैलेंस डिसेंटली फुलफिल हो रहा है, वो इंश्योर करेगा कि वी नॉट जो है वो वीडीसी से बड़ा होगा, तभी आपका इस इंटरवल में इंडक्टर एनर्जी रिलीज करेगा। और जब वी नॉट वीडीसी से बड़ा है तो सिंपल पावर बैलेंस से आई एल भी आई नॉट से बड़ा है, और जब आई एल आई नॉट से बड़ा है तो इस इंटरवल में कैपेसिटर एनर्जी स्टोर करेगा। So basically, in a boost converter, if you see, when the inductor is releasing energy, the capacitor is storing it, and when the inductor is storing energy, the capacitor is losing it. It's complementary. एक साइड से एनर्जी आती है, दूसरे साइड से एनर्जी it gets released and stored. The behavior of L and C is complementary in the circuit. Now moving on further, let's do a mathematical interpretation of the same thing. Also, if you see, I've rubbed the waveform, but if you see the capacitor current waveform, it is pure AC. जितना इसके अंडर एरिया होगा करंट सेकंड, वही एरिया यहाँ भी होगा। जैसे वोल्टेज अक्रॉस द इंडक्टर इज प्योर एसी एंड वोल्ट सेकंड बैलेंस उस पर इंप्लीमेंट होता है। सिमिलरली करंट जो होती है थ्रू कैपेसिटर, इट्स प्योर एसी, purely, it doesn't have a DC component, और current second balance इस पे implement होता है। both these things are they're dual in nature. This is for an inductor and this is for a capacitor, to ensure that they store energy and then they release it. They store and then they release equally. They store and then they release equally. Moving on, let's do the volt second balance for the capacitor, the inductor. पहले इंडक्टर की वोल्टेज जो थी, that was VDC, voltage across the inductor was VDC, and the time interval was DTS. Then the voltage across the inductor was VDC minus V naught, and the time interval was TS minus DTS. So this whole thing has to be 0. If I solve it, dVDC plus VDC minus V naught minus dVDC plus dV naught is equal to 0. TS को I cancelled it all together. This is 0, this is 0. Then V naught VDC is equal to V naught 1 minus D. So V naught is equal to VDC into divided by 1 minus D. ये वोल्ट सेकंड बैलेंस से मुझे वोल्टेज मिल गई। अगर मैं इनपुट आउटपुट पावर बैलेंस लगाऊं तो मैं आई एल और आई नॉट के बीच में भी सिमिलरली रिलेशनशिप ढूंढ सकती हूँ इसको उसमें यूज़ करके, और आई कैन डिराइव द सेम रिलेशनशिप फ्रॉम कैपेसिटर करंट सेकंड बैलेंस। कैपेसिटर करंट सेकंड बैलेंस क्या कहता है, वो वोल्ट सेकंड बैलेंस का ही डुअल है। इट सेज दैट इन सम इंटरवल से DTS and then TS, the capacitor may initially lose some energy and then it may gain some energy, but in a complete interval the net change in its energy, matlab it should not, the net change in its voltage delta V should be 0. When a capacitor is storing energy, its voltage is rising, and when it is losing energy, its voltage is falling. But एक पूरे साइकिल में नेट चेंज इन एनर्जी जो है, जितना एब्जॉर्ब किया उतना ही रिलीज किया, तो डेल्टा वी जो है टोटल वो 0 होना चाहिए। तो अगर आप सी डी वी बाई डी टी को आई सी मानते हो, डी वी को अगर 0 होना है यानी कि आई सी डी टी को 0 होना है। सो dV is equal to 0, यानी कि no net absorption और no net deliverance of energy। वो चीज़ अगर आपको रिप्रेजेंट करनी है, you have to represent it in the form of ICDT, ठीक है, करंट सेकंड बैलेंस। तो नेट एक कंप्लीट साइकिल में ICDT 0 होना चाहिए। Let's go back. The capacitor current in the first interval was I naught and the interval was DTS. And then it was IL minus I naught, where IL is basically nothing but the source current, and the interval was TS minus DTS. If we solve this further, DI naught plus IL minus I naught minus DIL plus DI naught is equal to 0. Right? Something is wrong. IL minus I naught, IL this is I naught, this is IL minus I naught, this is minus DIL, this is plus DI naught. Something went wrong. Wait a second. Capacitor was discharging, so it was minus I naught. Capacitor current पहले interval में, yeah. So this was IC and this was I naught. So obviously पहले interval में अगर हम ऐसे define करें तो IC was equal to minus I naught. तभी तो वो negative थी ना, capacitor was discharging. So this is minus I naught. यहाँ I've forgotten the minus over here. Yeah, I've forgotten the minus over here. So this is minus DI naught. This gets cancelled. This gets cancelled. Now if we solve further, I naught is equal to IL. IL is equal to I naught upon 1 minus D. और इससे पहले आपको मिला था V naught is equal to VDC upon 1 minus D. Obviously D जो है वो fractional values लेगा, तो 1 minus D will also have values which are fraction, and obviously the whole thing will imply that V naught is greater than VDC. The same thing is interpreted in terms of the currents, that IL is greater than I naught, जो कि मैंने आपको इससे पहले पावर बैलेंस से भी समझाया है कि वोल्टेज आउटपुट में बूस्ट होगी तो इनपुट की जो करंट है IL that is going to be boosted. So that's how power balance is maintained. So this was about their the relationship, the mathematical relationship of voltages and currents, जो current second balance और voltage second balance से satisfy होती हैं. If we want to plot this, if we plot this curve, voltage का ही curve plot करते हैं, current का भी obviously it will look the same. So if I have duty ratio, it is varying from 0 to 1, and I know that V naught is equal to VDC upon 1 minus D. So I have voltage V naught. When duty ratio is 0, that time voltage across the load is equal to VDC. And when duty ratio is 1, that time theoretically my load voltage is infinite, and this curve tends to infinity, something like this. So this is the shape of the curve. It goes on increasing as the duty ratio goes on increasing, and when the duty ratio hits 1, this output voltage theoretically it hits infinity, but it will never actually be infinity. In practical circuits, the voltage across the load is 7 to 8 times the voltage at the input. When we do a practical boost converter and we incorporate its non-idealities, at that point in time you will see that जितने अच्छे से आप इसको डिज़ाइन करोगे उतनी ज़्यादा वोल्टेज आप एक बूस्ट कन्वर्टर से एक्सट्रैक्ट कर सकते हो. So this basically depends upon how good your inductor design is, with the least possible internal resistance, devices with the least possible voltage drops and leakage currents. So this was about the boost converter. Also, let's quickly design its L and C, and in the next lecture we can do DCM and boundary conditions. So let me again draw the boost converter circuit. This is the boost inductance, this is the switch, the freewheeling diode, fast recovery diode, and then this is your capacitor across the load. Now let me design L first. I know that the inductor is governed by a simple equation, L di by dt is equal to voltage across the inductor. In the energy storage, I can take any interval 0 to dts or dts to ts. During 0 to dts it is convenient to take that interval. So उस टाइम पे आपके इंडक्टर में एनर्जी स्टोर हो रही होती है और आपका जो इंडक्टर है वो करंट जो है वो राइज हो रही होती है, और टोटल राइज इन करंट पीक टू पीक डेल्टा IL होता है. ठीक, तो दैट इज पीक टू पीक रिपल, दैट इज नेट चेंज इन करंट ड्यूरिंग दिस इंटरवल, दैट इज इक्वल टू डेल्टा IL. And let me take the whole interval as dts. जिस टाइम में डेल्टा IL की चेंज आती है उस टाइम पे your inductor voltage across the inductor is directly VDC. So this is VDC. So if I design L, it will be VDC into DTS divided by delta IL, right? Now I have also told you previously that it is always better to express it, design L in the form of delta IL upon IL, क्योंकि आपको delta IL generally नहीं दिया गया होता है बल्कि percentage ripple दिया गया होता है. So I want to modify this equation a bit so I get an expression in the form of delta IL upon IL as a fraction. Now let me modify this. I already have the design equation, the output voltage equations. V naught is equal to VDC upon 1 minus D, and IL, which is also IDC or I source, whatever you want to call it, is I naught upon 1 minus D. यहाँ पे VDC को मैं replace कर सकती हूँ V naught से. VDC is equal to V naught into 1 minus D. So I'm just replacing this VDC with V naught into 1 minus D. Then I still have another D over here and TS. And then I also have delta IL. इस V naught को मैं लिख सकती हूँ I naught into R. Let me say I naught into R. Or I naught को I can write IL into 1 minus D. So I can write this as IL into 1 minus D another, so make it 1 minus D square, and I can get this IL down here and make it this. So L is equal to R into 1 minus D whole square into DTS divided by delta IL upon IL. अब अगर मेरे पास percentage ripple होगा, I can use that simply over here and use the value of the load resistance and see how I can design L to achieve any, say, 5% ripple or 2% ripple or whatever percentage of ripple I want. So this is the design equation for L. Again, it tells you one thing. It tells you, अगर मैं TS को भी नीचे लेके जाऊँ, it tells you that if you want a low ripple, then design a high inductance. And if you don't want to design a high inductance, then do one thing, increase the switching frequency. Then for the same ripple, for the same low ripple, you will need a smaller inductance to get the same ripple. अगर आपने high switching frequency पे operate किया, because they have an inverse relationship, right? जो same चीज़ आपके buck converter में भी थी कि high switching frequency पे आपके inductor का size कम हो जाता है to achieve a small ripple. Or you can say that अगर आपने एक inductor use किया, इसको there are many ways of interval. आपने एक इंडक्टर बनाया, आपने से you used 1 millihenry. Okay, 1 millihenry you have used, and with that 1 millihenry at 1 kilohertz you are getting 5% ripple. But if with the same 1 millihenry you go to 20 kilohertz, your ripple will fall. क्योंकि आप ripple आप देखो, these are all interconnected. If you write this equation in terms of ripple, it will have an inverse relationship with frequency or with inductor. तो जनरली इट इज़ ऑलवेज डिज़ायर्ड कि आप हाई स्विचिंग फ्रीक्वेंसी में जाओ, लेकिन इतने ज़्यादा लॉसेस भी ना क्रिएट करो दैट यू बर्न आउट योर डिवाइस. सो हाई स्विचिंग फ्रीक्वेंसी अगेन डिज़ायरेबल इन बूस्ट कन्वर्टर, राइट? दिस वॉज अबाउट एल. नाउ लेट्स मूव टू सी एंड वील रैप अप दिस lecture. So this is about design of capacitance. Obviously capacitance will affect the ripple in load voltage. अगर आपने L का डिज़ाइन देखा तो it was affecting only the ripple in load current, inductor current, the ripple inductor current. Now let's see the design of L. So the design of C. If we see C dV by dt is equal to IC capacitor current, और कोई भी इंटरवल ले लो, प्रेफरेबली वील टेक द फर्स्ट इंटरवल, क्योंकि फर्स्ट इंटरवल में जो है आपकी कैपेसिटर करंट है वो डायरेक्टली आई नॉट माइनस ऑफ आई नॉट के बराबर होती है. तो लेट मी टेक सी, और पहला इंटरवल है 0 to DTS. उस टाइम पे कैपेसिटर की जो वोल्टेज है वो फॉल हो रही होती है, और उसमें टोटल पीक टू पीक फॉल आता है से डेल्टा वी का. तो कितना फॉल आपको मैग्नीट्यूड में चाहिए वो डेल्टा वी है. ज़्यादा नहीं चाहिए, बहुत कम चाहिए, 5% चाहिए, 2% चाहिए. तो दिस इज़ डेल्टा वी, और ये इंटरवल कितना है DTS. और इस टाइम पे आपकी IC क्या होती है, वो माइनस आई नॉट के बराबर होती है. ऑब्वियसली व्हेन यू आर डिजाइनिंग समथिंग टेक ओनली द मैग्नीट्यूड, सो टेक इट एज आई नॉट. सो C इज इक्वल टू आई नॉट, जिसको मैं V नॉट अपॉन आर भी कह सकती हूँ इंटू DTS डिवाइडेड बाई डेल्टा वी। और ये ऑटोमेटिकली डेल्टा वी क्या है, वी वोल्टेज अक्रॉस द कैपेसिटर विच इज़ वोल्टेज अक्रॉस द लोड। तो ये बन गया DTS अपॉन आर डेल्टा वी अपॉन वी नॉट। वेरी सिंपल इक्वेशन, ऑलरेडी आपको फ्रैक्शन के फॉर्म में आ गया, परसेंटेज रिपल के फॉर्म में आ गया। और ये भी आपको बोलता है कि जितनी हाई स्विचिंग फ्रीक्वेंसी उतना कम कैपेसिटर चाहिए फॉर द सेम अमाउंट ऑफ रिपल। या अगर आप एक कैपेसिटर डिजाइन करते हो, जैसे जैसे स्विचिंग फ्रीक्वेंसी बढ़ाओगे आपका रिपल कम होता जाएगा। तो देयर आर टू वेज ऑफ सीइंग इट। हायर स्विचिंग फ्रीक्वेंसीज गिव यू लेसर रिपल विद अ स्मॉलर कैपेसिटेंस। सो आप कैपेसिटेंस का साइज कम करने की कोशिश कर सकते हो विद दिस, और यू कैन से आप रिपल को ही कम करने की कोशिश कर रहे हो बाय इंक्रीजिंग द स्विचिंग फ्रीक्वेंसी। क्लासिक बिहेवियर ऑफ ऑल DC to DC कन्वर्टर्स irrespective ऑफ द टोपोलॉजी, वेदर इट्स बक बूस्ट और लेटर ऑन एनी ऑफ दोज, जितना हाई स्विचिंग फ्रीक्वेंसी में जाते हो उतने आपको कम छोटे साइज कैपेसिटेंस यूज़ करने पड़ते हैं। So this was about the boost converter, the design of L and C in detail, and some waveforms for continuous conduction mode. We talked about the current second balance, the voltage second balance, and how both L and C ensure that they store and release energy in complementary intervals, but they end up not consuming any excess of energy or not delivering any excess of energy. It's just storing and releasing, and that we ensure mathematically it's that balance is maintained through the volt second or current second balance. दोनों से हमने equations के form में इसको interpret किया, and we also saw the behavior of L and C with respect to switching frequency and ripple in load voltage and load current. So yeah, that is it. अगर आप यहाँ देखोगे कैपेसिटर के इक्वेशन में आपको L कहीं नहीं मिल रहा है, अनलाइक अ बक कन्वर्टर। वहाँ बक कन्वर्टर में L और C दोनों ही आपके आउटपुट वोल्टेज की रिपल को अफेक्ट करते थे। यहाँ पे सिर्फ आपका कैपेसिटर आपके आउटपुट वोल्टेज की रिपल को अफेक्ट कर रहा है। सो इफ़ यू बेसिकली सी DC to DC converter, every year I teach it, I personally learn something new while just talking about it. There are many ways of interpreting these small equations. I hope you find your own new ways of interpreting them. In the next lecture, we'll move on to DCM and then the boundary condition and some questions on, and then we can move to discussing those questions in the doubt clearing sessions. Wishing you all the best. I hope this was a comprehensive lecture. Keep me posted and please give me your feedback. Thank you.